Good morning. This is Unlock Circuits 18EC42 Module 2 Lecture 3 Frequency Response of CS Amplifier. So this is the part 1 of the lecture where we will consider the three bands of the frequency response and also the high frequency response. In the part 2 we will discuss about the low frequency response of the CS amplifier. So first the three frequency bands which we will consider over here. So this gives us the common source or what is known as the CS amplifier with the so to say the coupling capacitors CC1 and CC2 which are used to separate the DC with the AC, and then you have the bypass capacitor which is the CS capacitor which is used for again bypassing the DC. That just means that at the time of amplification, the what you call feedback is not going to work out very well. But for the DC, the feedback is considered so that stabilization is improved. This is the signal source which is there as it is, and this is the load which is there, and rest of the thing is a bias circuit, or rather constant current source biasing which we are using over here compared to what we have considered in the earlier class. Okay, so now we have the three frequency bands. You can see that this gives you the frequency response of the circuit, where this part is the low frequency, this part is the high frequency band, and you have in the middle the what you call mid band. So the mid-band value we can find a little later, but for the present we can consider that the figure B, which we have considered here, this is the figure B, has overall voltage gain GV, including the signal. GV is the overall voltage gain, including the signal source, versus the frequency of a common source amplifier. So on the x-axis you have the frequency, and here you have the GV, which is V0 by Vc. There are three regions in this: the midband region where the gain is almost constant over a wide frequency band. So you can see that the gain is constant in the midband, almost constant in the midband. The midband gain is the value equal to AM equal to GV equal to V0 by Vc is equal to minus of Rg by Rg plus Rsig into Gm R0 Rd RL, and this can be considered as RL dash. We'll see how we can derive this equation a little later, but for the present we can consider AM as this. The gain falls off at the signal frequencies below and above the midband. So below the midband and above the midband, you can see that the value of the gain is reducing or falling because of the different capacitor effects which are there. During low frequency band, the fall off is due to the CC1, CC2, and CS at low frequencies. So coupling capacitor and the what you call the bypass capacitor CS, these two are coupling capacitor, this is the bypass capacitor. These are responsible for the gain fall off at low frequency. So that is what is mentioned over here. You can see that gain falls off due to the effect of CC1, CC2, and the CS is what is being mentioned here in the low frequency band. Similarly, in the high frequency band, the gain falls off due to the effect of CGS and CGD. These are the internal capacitances which are present in the Mosfet. Due to the Mosfet, there are internal capacitances, and due to those internal capacitances, we see that the high gain is falling in the high frequency band. So compared to the mid band, what you call, we have the mid-band gain, which we generally call it as AM by what you call AM, and the frequency FL and FH are the frequencies at which we have the gain, which is 3 dB less than the mid-band gain, which generally can be represented as gain of root of AM by root 2, mod of AM by root 2. And if you take the 20 log of this, then you will get exactly the value, which is minus 3 dB. So that is 3 dB less. You take the 20 dB of this value, 20 dB of AM by 1 by root 2, ideally speaking, then you'll get minus 3. And that is 3 dB below, and hence they are known as the lower 3 dB and upper 3 dB frequencies. Uh, that is just means that at this point we are talking about the point which is this and this, at which it is 3 dB less, and this is the lower 3 dB frequency, and this is the upper 3 dB or higher 3 dB frequency. Uh, from the mid-band gain, the value of the gain at this point and at this point is 3 dB below the uh, peak. And magnitude wise, you can just consider it as, this is, if you consider this as AM, this point will be AM by root 2. So you can consider in terms of direct values AM by root 2, or in terms of dBs as AM minus 3 dB, that is 3 dB less. So the difference between these two frequencies, FH and FL, is known as the bandwidth, and generally FL is very small compared to FH. Therefore, bandwidth can always be said as equal to the high frequency, what we call 3 dB high frequency, or upper 3 dB frequency, which is FH. So there is a figure of merit of the amplifier, which is generally known as the gain bandwidth the product, the gain which is midband gain and the bandwidth which is FH, you can consider. So both of them together, AM into the bandwidth, will give us the gain bandwidth product. So this just gives us the equivalent circuit of whatever circuit we have mentioned over here. Same things are there, right? So the coupling capacitors have no effect in during the high frequency response. Therefore, we just remove them, because of the sole reason that the when high frequency is there, then due to high frequency, 1 by omega c will be very, very small. So the effect of this will be nothing. And again, this is 1 by omega cc2. Omega is very high. If you say high frequency, the impedance due to that will be 0. And again, when we have the high frequency over here, when you have the high frequency, the impedance due to this again also will be 0. That means effectively the constant current source is shorted during the what you call high frequency, and hence if this has, the constant current source has no role to play as far as the high frequency is concerned, except that for biasing it is useful. So this is a constant current source biasing circuit. Then rest of the thing is just the same. The RSIG and the VSIG are due to the source, and we have RG connected in the figure over here, and RL is there as it is, then the RD in the analysis, AC analysis, VDD will go to ground, and so RD will come in parallel with RL. That's why we have RD in parallel with RL. The rest of the thing over here is nothing but the high frequency equivalent circuit with the CGS and CGD and the constant, current source, dependent current source rather, which is GM-VGS, which is dependent upon the input voltage VGS and the output resistance of the Mosfet, which is known as R0. So this block totally is the equivalent circuit, high frequency equivalent circuit of the hybrid, which is known as hybrid pi model generally of the Mosfet. So now in the figure below, what we have done is just replaced this input side, this part of it, that is the Vsig, Rsig and Rg, by means of its Thevenin's equivalent voltage, Thevenin's equivalent resistance. When we talk about the Thevenin's equivalent resistance of this, then the voltage source is shorted, so Rsig and Rg will come in parallel, and that will be the equivalent Thevenin's equivalent resistance, and that is this Rsig dash, Rsig in parallel with Rg. Then the what you call Thevenin's voltage between this and this terminals. So Thevenin's equivalent between this and this terminals is what we need to find out. The Thevenin's resistance, equivalent resistance is this in parallel with this, because this is shorted, and Thevenin's equivalent voltage between this and this terminals looking in this side, that is replacing this, is basically if you take it over here, this is a this two resistors will just form a voltage divider network, and hence this voltage Vsig is divided between the two. So that means Vsig multiplied by Rg divided by Rg plus Rsig is the value which we have over here, or you can consider it something like this. The current flowing through this is considered as Vsig divided by Rsig plus Rg, and that current multiplied by Rg will give me the voltage across Rg, that is the Thevenin's equivalent voltage, and that is what is being mentioned over here. The rest of the thing over here is as it is, over here, and again the resistors R0, Rd and RL, all these three together are considered are in parallel, and hence they can just be replaced by a single resistance which is known as RL dash. So this parallel combination of this is RL dash. RL dash is equal to R0 in parallel with Rd in parallel with RL. The GMVGS and the other capacitors are kept as it is. Now, between the G and the D, the gate and the drain, this is the source point, right? And this is the drain point, and this is the gate point. Between the gate and the drain, we have the capacitor here. Now, this capacitor can be replaced by two different capacitors, one on the input side and another on the output side. The output side capacitance is neglected, only the input side capacitance is generally considered, and that is due to the Miller's theorem, or what is known as Miller's effect, and that will be found, can be easily found by just writing that this CGD, if it is brought on this side, then that will be CGD into 1 plus GM RL dash, and that can be derived very easily, and that is what we are trying to do over here. So this IGD is equal to the value being mentioned over here, and that can be considered something like this. The IGD is the current which is flowing through this, and that is equal to the voltage here across the CGD can be considered as IGD multiplied by the impedance due to this. The impedance due to this is 1 by S CGD multiplied by ID. That's the value there. That is the impedance, that is the voltage across this, and that is equal to VGS minus V0. VGS minus V0 is equal to IDS divided by S CGD. And once we have that, IGD will be naturally S CGD multiplied by the VGS minus V0. And that is what is mentioned over here. Now, we can replace this V0 by means of the value over here. So, so we are just replaced in this figure. You can see here, this capacitor is replaced, transformed onto the input side, and also, really speaking, it is transformed onto the output side, but the output side capacitance is so small that it is generally neglected, and we are not considering it here, but only considering on this side. So now from here, you can find out the value of V naught. So this current which is flowing down here will be flowing up because the loop current will be like this. The loop current will be flowing like this. And the current naturally GMVGS is flowing through RL dash in the upward direction. And hence, that is from the ground to the V naught. Hence, the value of V naught will be minus GM RL dash into VGS. So V naught can be replaced in the next, is replaced by, V naught is replaced by minus GM RL dash VGS. So out of these two, you can take out the VGS common, and minus into minus will become plus. So therefore, it will become SCGD 1 plus GMRL dash into VGS. So the VGS divided by the VGS divided by the IGD will be the value 1 by this whole thing, 1 by this whole thing. So it is equivalent to saying that 1 by this whole thing means that it is what you call the impedance. 1 by this whole thing is the impedance due to the capacitance, which is this. So we can just replace this by a equivalent capacitance. From the above, we can get the expression for the equivalent capacitance as CGD multiplied by 1 plus GM RL dash. So that is what is there over here, and hence in the figure also we are just calling this as the equivalent capacitance, and the value of that is this. And naturally, because these two are in parallel, they'll get added up and we'll get C in is equal to CGS plus the C equivalent, that is CGS uh, plus C equivalent being mentioned over here, that is equal to CGS plus CGD into 1 plus GM RL dash. So having mentioned that, we can use the figure C again. So this is a capacitance, total capacitance equal to C in, that is CGS plus CGD into 1 plus GMRL dash. So now this is, R sig dash and C in will become a high pass filter, or what is known as an integrator. And again, this voltage which is there is distributed between this R sig dash and the total capacitance of this, which is known as C in. So we can again write the what you call the expression for the VGS over here, the VGS over here across the capacitance will be equal to this multiplied by the impedance due to this divided by the impedance of this plus the impedance due to this. So further simplification of that will just lead us to this expression, wherein we can just write S equal to j omega, and omega naught is equal to 1 by C in R sig dash. So this you can consider as an exercise, and you can derive this. It's not a difficult one at all, because it is just can be derived by considering that this voltage divided by the R sig plus the impedance due to this, which is 1 by SCN, multiplied by again the value which is the impedance due to this, that is 1 by SCN. Then further simplification can be done, and we will get, after substituting these two values, this particular expression. So from this you can what you call the VGS value can be substituted into the expression for V naught. So also we can see from the figure C, V naught is equal to minus GMRL dash VGS. This we have already found, and this V naught minus GMRL dash in this whatever VGS we have derived now can be substituted, and hence we get after substituting this into this, we will get here the value which is something like this. So substituting that 1 in 2, we get this expression V naught by V sig is equal to minus Rg by Rg plus R sig Gm RL dash 1 by 1 plus S by omega naught or omega h, omega naught or omega h. Now this value is the GV which we have, which this can be expressed over here as an expression like this. So this expression can just be replaced by AM, and this is a single time constant or single pole circuit. This is a single pole circuit. You have a single S. This is an equation of S in the so to say 1 degree, and hence this is a single pole or single time constant, uh, and this is the midband gain, because when this quantity is equal to 0, then this will be AM by 1, that is equal to AM. So therefore we can just say that this expression, the equation for this, this just corresponds to the AM itself. So having written this, we can just say that this WH is nothing but 1 by C in R sig dash, which we have already considered over here. Omega naught is equal to omega h is equal to 1 by C in R sig dash. And from this, we can replace this WH by means of 2 pi FH, or FH is equal to WH by 2 pi. Therefore, that will be 1 by 2 pi C in R sig dash. So the high frequency, so to say 3 dB upper frequency is equal to 1 by 2 pi C in R sig dash. So from this, we can make certain observations, and the observations are the upper 3 dB frequency is determined by the interaction of R sig dash equal to R sig in parallel with Rg and C in, which is the sum of these two. So that's what is there in this. We have here, the what you call, if you see this over here, R sig dash is being mentioned in the FH here, and we have C in. So FH is inversely proportional to R sig dash and the C in, and that is what we are telling over here. Generally, the Rg is very, very large compared to R sig, so R sig dash can be considered almost equal to R sig. And further, because of this reason, we can say that if R sig is, R sig or R sig dash is, very large, then the FH will become lowered. So if the R sig dash is very large, R sig dash equal to R sig is very large, then FH will get lowered. So we don't want FH to be very small. We want FH, the upper 3 dB frequency, to be as large as possible. So therefore, the value of the R sig dash or R sig should be as small as possible, for FH to be very large. So R sig is generally should be very small. Otherwise, the FH will be reduced. Okay. Then the second point is the total input capacitance seen is usually dominated by the C equivalent. So Cin, we have already written the expression for that. Cin is here, mentioned over here, and this is dominated by this, even though we have CGD very small compared to the CGS. We see that we have a factor which is multiplied with the value of CGD, that is 1 plus GMRL dash, which is generally equal to the, most of the time, the midband gain, almost equal to the midband gain. So this is the midband gain almost multiplied by CGD, which will be quite huge, and hence the Cn is dominated by this figure rather than this figure. So therefore, we see that we have this generally the what you call Cin is totally with respect to the CGD rather than with anything else. The multiplication effect that CGT undergoes comes about because it is connected between two nodes whose voltages are related by a large negative gain, that is minus GMRL dash. Now, this is, as we have discussed earlier also, due to the Miller's theorem or Miller effect. And this Miller effect generally causes the CS amplifier to have a large total input capacitance Cin. And if Cin is large, then naturally again we have the lowering of the frequency. So for we would like that FH should be very large. If FH is very large, Cin should be small, RSig dash should be small. RSig dash should be small means RSig itself should be small, and Cin small means naturally the what you call CGD should be very small, because CGD is multiplied by 1 plus GMRL dash, which is the midband, almost equal to the midband gain. So we would like that the midband gain is large, but CGD, if it is small, then only the FH will be what you call large. Otherwise, FH will get lower. So to extend the high frequency response of MOSFET amplifier, we have to find configurations in which the Miller effect is absent or at least reduced. So only if if you want a better high frequency response, or so to say larger value of FH, then we should find configurations where this Miller effect is absent or reduced. So the above analysis is basically a single time constant, a single time constant circuit. STC is single time constant circuit, or single pole response. And this is a simplified one because I already said that the capacitor over here, which is CGD, should be replaced by two capacitors, one on the input side and another on the output side. The output side capacitance is negligible, we have considered, but however it is there. So we might get another pole on the output side, one pole on the input side and another pole on the output side. So that is the perfect analysis if we take two poles, but we are still for our purpose we are just considering only a single pole. So specifically it is based on neglecting IGD relative to GM-VGS. It can be considered in this way also, that we are neglecting IGD relative to the VGS into GM into VGS, an assumption that applies well at frequencies not too much higher than FH. A more exact analysis can be done, and this is out of the scope of our syllabus. However, whatever results we have got are sufficient for our consideration. So in the part 2, we will consider the low frequency response.